answer as well, in the same rule. Okay. So, interrupt me if you have any questions. I'm also a PhD student with Erwin. So yeah, if you also have questions about the research or anything like that, I'm happy to answer. So today what we will do will be, so first we will go through an example of how you can apply the two-component analysis that you developed the last time in a concrete example. So we will look at the biophysical two-component model. After that, we will move to a kind of a new topic, which is like game theory and how this can connect to phenomena like condensation and topological phases. And after that, we will start the diffusion equation, which is space. Because so far, you have seen everything in a zero-dimensional system, and then we will start to see how you can actually couple different points in space. Okay, so this is the program for today. So we start just looking again at the classification. So when you have two-component systems, and you've seen usually when you do linear stability analysis, then you look at the Jacobian, right, at the fixed point, and I'm pretty sure you saw a drawing like this one. So you have delta here, so the determinant and the trace of the Jacobian, right? And then you have something like that. And you can have here stable oscillations. Here you would have unstable oscillations. Here you would have the so-called centers. Okay. Then here your fixed point would be unstable. On the other side, stable. Okay. Right? And then if you have that the determinant is negative, you always have something unstable, right? In different directions. So it would look something like that. Okay? Or similarly. Okay, great. So I hope this is clear to all of you. And now the question is, whenever you do linear stability analysis, usually you get an information that is very local, right? So you just stay very close to the fixed point. And then you know if you're getting out of the fixed point or you're getting in the fixed point and in which direction. This is pretty much all you can get from linear stability analysis. And then when we would like to have a bit more of a global information, it's not so easy. So usually the things you do is, well, you have to simulate the whole system. But for some cases, especially for two-component systems, there is one theorem that can help us a lot, and this is called the Poincaré-Bendixson Theorem. Okay? So we will discuss first this theorem, and then we will see an example for a two-component system where we can apply the theorem. Okay? So this is a beautiful theorem. So I will give sort of a physicist formulation of the theorem. So obviously, if you want to do it properly, there are a lot of assumptions and so on, but I think this is enough for us. So this is what it says. If for t greater or equal than some t0, okay, we have that an orbit is bounded, so we know it doesn't leave a certain region. Okay. And on top, it does not approach any steady state, so any singular point. So then the orbit will be either a limit cycle or it will approach a limit cycle. So this is the theorem. Okay, let's write it down and then we discuss about it a bit. Okay, so is the theorem clear in terms of its formulation? Okay. So what is this theorem ruling out? Do you have any idea? So what does it say that it cannot happen? So we already, yeah?
Any non-periodic endless going on motion?
Exactly, which is usually also called chaos. So this is what it says, and this is why it's so famous that you don't have chaos in 2 dimensions, pretty much. So either you have a steady state, or if you have a closed orbit, then you will end up in a limit cycle. And this for us, it's kind of important because it happens often that we have fixed points that get unstable, and then somehow if we manage to close the region, and we find a region that is bound in phase space, which is usually the case because in physics you don't want things that go to infinity, right? So you have like some bound region, and then you can say, oh, I have a limit cycle. It's enough to have that the fixed point in there is unstable, right? Yeah?
What is a limit cycle?
Oh, okay, you haven't seen this. So a limit cycle is a periodic orbit.
Okay.
Yeah?
Can you expand on the idea of a singular point? Is this a fixed point or?
Yeah, here we mean really like a fixed point, so a steady state that is stable. You can just read it as that. Yeah, and the limit cycle now we will see exactly what it means, but it's an oscillation. So I think you discussed about off bifurcation last time, right? Exactly. So by limit cycle I really just mean a periodic orbit. All right, so let's see this explicit example together. So we discussed these concepts, and it will become much clearer, I'm sure. So we will choose a biophysical example, which is the RhoGTPase cycle. Okay. So RhoGTPases are a family of proteins, and they control many cellular processes. And the reason they can do that is that they can switch between 2 states. And also they can switch between membrane and cytosolic state. Okay, so we have a membrane. So I'm not sure how familiar we are with the cell, but cells have membranes, right? So lipid bilayers, and a lot of proteins can actually bound to those membranes. This is crucial because this allows them to form nice patterns on the membrane, okay? And this family of proteins, or RhoGTPase, they are very important in controlling how proteins attach and detach and how they form patterns on the membranes. So for example, for actin waves, it's very crucial the role of this family of proteins. So we'll just look at a very minimal model for how they behave. So we have a membrane. Okay, here this is the cytosol. And then we have, this is a RhoGTP, okay, that can switch into a RhoGTP, so an energetic state, okay, and it will do this thanks to some proteins that are called guanine nucleotide exchange factors, but we'll just call this rate KGEP. Okay. Once it's bound on the membrane, it is in an active state. What it can do, well, it can detach. And it also immediately, so we imagine that it hydrolyzes and detaches immediately, okay? So this will be again a RhoGTP state. Okay, and this again, it's controlled by proteins, which are called GTPase activating proteins, but we will just call this KGAP. Okay. And then we have that this can attach K on and detach K off. Okay, so this is a very minimal cycle. So what we want, what we will make nonlinear is this process here, okay? Because what happens is that indeed the proteins that mediate the switch from GTP to GTP are recruited by GTP itself. Okay, so the more GTP you have, the more you will get, kind of idea. So this will actually be KGEP of MT. In my notation, M is membrane bound and C is cytosolic species. Okay, so this will be with some linear rate, basal rate, plus a nonlinearity. Okay. So now, in principle, already from this reaction scheme, you should be able to write down the time evolution of the proteins. Okay? I think you've seen this in a couple of exercises, but let's do this together. So, time evolution of MT. So what does it do? We see, right, it increases through this process and decreases through this process. Right? So what does this mean? Well, so linear detachment plus what we just said, so it's KGEP multiplying M E. Right? You get the logic. Mm-hmm. Now again, the same for MD. It will increase through attachment from the cytosol. It can decrease through detachment into the cytosol. And it can also decrease through switch into a GTP state. So this is just what we have to write down here. Okay, so now the same game for the cytosolic species. So this is our set of equations. And before I advertised, we were looking at a two-component system, right? But this looks more like a three-component system. Any guess, how can we make this into a two-component system?
Mass conservation.
Yeah, exactly. Mass conservation. So how do we see that this is mass conserving? Well, if you just sum these three equations, you get 0, right? So we can introduce M, which is equal to Cp plus Mt plus Mv. So now I will simplify the equations a lot. So what I will do, I will set K on to 1. This accounts for rescaling time. We will just simplify K off to 0. And then for simplicity, we will set, K basal and K O2 to 1. Okay, so in the end we get something like that. You can do the rescaling yourself. This is always a useful exercise. Okay, yeah, well now mu reads actually, it's quite an important parameter, so I kept it like that. And this is like k get over k on. Okay, so what are the null lines for this system? Well, we just have to set the right-hand side of these equations to 0, right? So I'll just write them here. All right, so we have these two null lines. Now I want to plot them in space and to see what kind of fixed point we could have. Okay, then you would get the one for MD that looks a bit like this. So now we said we want to apply the Poincaré-Bendixson Theorem. So what we need to find a region where we know our orbit, can you see? So we know that our orbit should not leave the space. Maybe we write the nuclides, but I mean, this is the shape they have, but what is important is that we understand what happens around them, so around the fixed point, because we want to find a bound region. So what happens? Well, you know that on the nuclines, the orbit will only go in one specific direction, right? And now here, for example, we have, this is md equal to 0. For the dynamics of md going to 0, this is for the dynamics of mt going to 0, if I did this right. So here mt in this part should be increasing, right? And whereas below should be decreasing. And then we have for MD, it should be something like that. You can check it for yourself, but just looking at above and below the nucline or left and right. Yeah, above and below the nucline, you check where it has a positive sign and where it has a negative sign. But just from looking at this various sort of heuristic argument, we see that if we draw something like that, well, then our orbit should not leave this space. Okay? So this is very heuristic, but it works, right? And then we have a fixed point here. We know they should cross. But then, to be sure, we have a limit cycle, because we want an oscillation. What do we have to check now?
It's unstable.
That is unstable, exactly. Okay. So how do we do that? We have to look at the delta and the tau from there, right? So from this drawing here, and we want to be we want oscillation, so we actually want to be somewhere here, right? So those are spiraling out, and we want this spiral to approach an orbit, which is a limit cycle, which is what we're looking for. Okay? So let's write down how they look. Of course, I will skip the explicit calculation, but really you can easily fill in the gaps. Okay? So I will just write tau and delta. So this is the expression for tau, this is the expression for delta. As we said, we want to be in a region where we have oscillations. So we want to be somewhere here. So definitely we want this to be a positive tau, right? Because we said we want those to be unstable, otherwise we cannot use the theorem. So we want tau to be bigger than 0. Let's look at this expression. Here we have this, maybe I get a color. So here we have that this is negative, we have that this is negative and this is negative, right? And then the only thing that can get positive is this term here. And this is MT star, MD star. So we can look at the note lines. I write them here again. Okay, so if we plug in this nuclei, we know at the fixed point both have to be satisfied. So if we plug in this for MD here, we get mu 2 mu MT squared over 1 plus MT squared. And this quantity for MT smaller than 1 would be smaller than 1. So here it's multiplying by mu. You can plot this function for yourself. But MT squared over 1 plus MT squared multiplied by 2 is smaller than 1 for MT smaller than 1. Okay? So this tells us that if MT is smaller than 1, this quantity will never be positive. Okay? So therefore, we can assume that in order to have an oscillation, we definitely need MT to be bigger than 1. Clear? Okay. So we ask MT to be bigger than 1, then this helps us here, because therefore we have that the determinant is always positive. Okay, because the denominator is the only thing that can get negative, and for MT bigger than 1, this will be positive. So we said, okay, so our condition here to make this, to be sure this is positive, is really that MT has to be bigger than 1. But then we have that delta is always positive, so we are always in the upper quadrants here, right? So this is nice. And now we want to know where does pretty much, okay, we want to know where is the off bifurcation. So where do we start having that our fixed point from stable becomes unstable? So we need to set tau to 0, okay? So for this, and of course also those two have to be equal to 0, okay? So we have 1, we have 2, and we have 3, which is just tau equal to 0. And if we use these three conditions, we manage numerically to find the parameter in which this happens. So we can plot them. So we have here mu, here n, and you find something like this, pretty much. Okay? And then if we want, we can also analytically find those boundaries. This is done in the lecture notes. So you can find nice approximations for this function and this function. And the way to do this is to say, well, let's look at mu very big. This will be included in this space of oscillations. And then you can get analytical expressions for it. But I think what is interesting now, if we need to take care of the physics, okay? We see that for mu very big, this will be a region of oscillations. Okay, and to get this, we really rely heavily on the Poincaré-Bendixson Theorem, because we are only looking at here linear stability, right? We're not looking at any global quantity, but in the back of our mind, there is the Poincaré-Bendixson Theorem that says if you have an unstable fixed point, you must have limit cycles, right? So it's enough here to get local information and get, like, actually global limit cycles. This is quite rare, actually, to have something like that. And then interestingly, if we try to think about the physics, well, we say, for mu very big, what does it mean? And then we look at what was our mu. And our mu was k gap over k on. So it means that a lot of our proteins are detaching from the membrane and going into the cytosol. So interestingly, we can even get a bit of an intuition of what this means. So we need to have a lot of material in the cytosol. Okay? So you see how from a simple model and a bit of analytics, we actually got an insight on when we should expect oscillations for the RhoGTPase cycle. Okay, very well. Now we will introduce a very different topic. So for this, we look at the slide at the moment. Yeah,
Before the topic, can you once again explain what the limitations were for tau and for delta coming from here, from the two component systems?
The limitations?
Yes.
So here I just wrote the explicit form of them, so just as it looks. And then I just look at some considerations of, okay, I want an unstable fixed point, and I want to have a limit cycle. So I want the imaginary part to be also different from 0. So I want to be somewhere in the tau greater than 0, delta greater than 0 quadrant, right?
Okay.
Where you can have unstable fixed points that spiral. So you have like a spiraling outwards orbits from the fixed point. So that's what we would like to have. So we need tau to be greater than 0, right? And then you look at the explicit form of tau, and you see that the only term that can get positive is this term. And then you do some analytical considerations from how this function looks like. So you need this to be bigger than mu, right? At least. I mean, more because you have other negative terms, but at least bigger than mu. And for this to happen, you need that mt is greater than 1, just because of the explicit form of the function. And then, since you know that mt has to be greater than 1, you know that delta is always positive. Right? And then you can just study when tau becomes positive, because you have delta is always positive, so my up bifurcation is really just given by looking at the condition tau equal to 0. Okay, and then that's what you plot here.
Okay, thank you.
Yeah, so this line is just tau equal to 0. Yeah.
So, I don't know if I remember correctly, but on the upper plane, to the right, the states are like stable, the fixed point is stable or unstable?
Unstable.
Unstable. So, why do we want like exactly spiraling? Can we have like also like non-spiral fixed, like unstable fixed point, and this would also guarantee us the limit cycles?
Yes, so technically yes, it cannot really happen for the kind of system we have, but we are not really looking at the full space, we're looking at the transition between, so we're looking at the up bifurcation. So we are just interested at when this can happen. So pretty much we are looking at here. We're looking at just very close here. And you're just saying, well, when do I move from a stable to an unstable point? Okay? So this would be even further away. But now we're just looking at this region here, and we kind of know, because of how it looks like, that if it's unstable, there must be a limit cycle. So we will always end up somewhere here.
Yeah, but in principle, we could start from this outer right region.
Yes, in principle, yes, but then of course, you don't always have all possibilities when you have a two-component system, right? Then it depends on solving the equations, you find which cases actually happen or don't happen, okay? And it's a pretty good guess to say we will stay within here, because we know from heuristics that we must have a limit cycle, so you must have something that is orbiting around, so the imaginary part has to be different from 0.
Okay.
Here?
Just to make sure, so for example, we start from a really upper right region, and then we might end up in an unstable outgoing spiral, then it's also allowed to have some unbounded orbits, right? It's just not we want to find, for example.
Yeah, so if you find an unstable fixed point, in principle, you could definitely have that stuff is just flowing upwards. But here we created like a sort of a boundary where we know the orbit cannot get out. So that's why. I mean, you could have something weirder. So you could have something like, I don't know, this gets out, and then at some point, if there is another fixed point, then you could have a different kind of limit cycles. But when you have a system like that, and the fixed point is unstable, then it's enough to know it's unstable. Then I draw a small circle around it. Okay, I draw a small circle around it. I have this bound region around here. And then I use Poincaré-Bendixson Theorem. There is a limit cycle. There is a limit cycle somewhere here. So we are guaranteed that there is one. Other questions? So it's important that you get into the way of reasoning, kind of. It takes some exercise, but it's really important to keep in mind what are the possibilities, and then, yeah, in some cases also Poincaré-Bendixson, which, to be fair, in physics, you always want bound regions. So this should always work in a way, because otherwise we would start from some physical density and then go to infinite densities. We never want to go to infinite densities, right? This wouldn't be physical at all.
I still don't fully understand why do we know that around the fixed point we have a spiraling behavior and not like straight flowing out, and the spiraling starts like outside the inner.
You could have that as well. You could have that as well.
Okay.
Technically, right?
It really doesn't matter. We don't take the spiral into consideration at all in this.
No, we are just saying that it has to be unstable here. We're not saying anything more. We are just saying we know delta is positive. To make it unstable, we want tau to be positive. That's all we are doing.
And also, this is the linear analysis. And here, that only is correct if you are very close to the fixed point. So if you can start with straight lines, and then if you go out, it can turn into a spiral.
Definitely.
Because it's non-linear behavior afterwards.
Yeah. So this is why we need the Poincaré-Bendixson theorem. But intuitively, it's nice if close to the fixed point you also have something that oscillates. At some point, it has to start oscillating, right? Because it has to reach a limit cycle. It could be that close to the fixed point, it just goes out and then starts oscillating. It would be a bit weird. But that's not important. It's just important that this is unstable. Okay. So it's clear. You'll do plenty of exercises on these things. So I think it will become clearer the more you work with this. Okay. So maybe then we introduce the new topic before the break, and then we get into the details after the break. So this is a bit of a new topic. So this is really going a bit beyond what we discussed so far. So the idea is to see, oh, maybe I should turn off the light so you can see better. Yeah. So the idea is to see how we can use this dynamical system to actually study like systems that go way beyond protein patterns or just strictly biophysical examples. Okay. So one application is that of game theory. Well, game theories are used a lot in economics, can also be used in biophysics. It's just a bit of a different framework, a different way to think about things. And indeed, for this specific example, we will look at called the antisymmetric Lotka-Volterra equation. You also have a phenomenon that looks a lot like Bose-Einstein condensation, and you could also study topological phase transitions. So it's actually interconnected to a lot of physics. So first of all, what are zero-sum games? So zero-sum games are games in which the loss of a player is the win of the other player. So the sum is zero. One well-known example is rock, paper, scissors. I'm sure you know this game. So now you have to get into the mindset that now what we want to study is the evolution of the strategies. So the strategies will be our components now. Okay, not the protein species, but the strategy. And now, what is a simple strategy you could choose? It's only plain paper, only plain scissors, only plain rock. This is a strategy, right? One of those three. So we say we have three strategies. But this can be generalized. And a famous example that Erwin loves is that of rock, paper, scissors, lizard, Spock. I don't know how many of you are familiar with this game. It's literally, so you see here the paper that Erwin wrote about this kind of systems. So here is the bibliographer below. And in this paper, there is an actual citation to the Big Bang Theory. So this is the video. Erwin loves to show this video.
How about you decide this with rock, paper, scissors, lizard, Spock?
What the frig is that?
Rock, paper, scissors, lizard, Spock was created by internet pioneer Sam Cass as an improvement on the classic game Rock, Paper, Scissors. All hail Sam Cass. Hail.
How does it work?
Oh, it's very simple. Scissors cuts paper, paper covers rock. Rock crushes lizard, lizard poisons Spock. Spock smashes scissors, scissors decapitates lizard, lizard eats paper, paper disproves Spock, Spock vaporizes rock, and as it always has, rock crushes scissors.
I'm sorry, can you repeat that?
Well, of course. Scissors cuts paper, paper covers rock. Rock crushes lizard, lizard poisons Spock. Spock smashes scissors, scissors decapitates lizard, lizard eats paper, paper disproves Spock, Spock vaporizes rock, and as it always has, rock crushes scissors.
Almost got it. One more time?
Surely. Scissors cuts paper, paper covers rock.
Okay, I think we don't need it one more time. I think you got the idea. So you can actually have as many strategies as you want, and you can just go on generalizing. So you can also obviously make S go into infinity, right? If you just want to be a physicist about it. But let's maybe go a bit more into detail in the rock, paper, scissors game. So we'll get into how we should be thinking about this. So we think this is a reaction kinetics. So this is a bit what I drew before for the RhoGTPase. So we call this a replicator dynamics, meaning you're playing a strategy and then you play against another strategy. So for example, imagine rock plays against scissors, and who wins is, no, okay, here it's rock, but rock smashes scissors, right? So then, since you replicate the strategy that won, you will have two rocks. Okay, is this clear? So you just adopt the strategy that wins. This is the dynamics that we are postulating here. And you can do it for each interaction. So you effectively imagine the strategies interacting in this replicator dynamics. Right? So you can write this as a dynamical system. This is exactly what we did before for all the different strategies. And then you can write this as a linear system. And imagine what? Well, okay, we can see this as a network. So this is similar to the drawing I did before with the membrane and the cytosol. And you can find, again, like unit cycles and orbits that are circulating. All right, so then I will say we have maybe a 10 minutes break, and then we go into the maths of how we can study such a system. So see you in 10 minutes.